Geodesics play a very important role in the theory of gravity as defined in the general theory of relativity. They are the paths of the free observers. Observers that are not subject to any other force follow geodesics in space-time. As we will see, geodesics have the property of being, at least locally, the straightest possible lines of minimal length for space-like geodesics, or maximal proper times. Geodesics also gives a way so that we can detect gravity. As we will see in the following video, curvature makes initially parallel geodesics to deviate from each other, and that is interpreted by observers as being the effect of gravity on them. We will define geodesics in terms of given parallel transport or a covariant derivative on a manifold, but we will see that also geodesics determine parallel transport and covariant derivative. Finally, we want also to discuss how to use geodesics to define a special set of inertial frames that is given in terms of coordinates which are called Riemann normal coordinates. Let's start with the definition. A curve is a geodesic if it parallel transports its tangent vector. We have defined parallel transport along a curve to be given by vectors that are invariant under the directional derivative along the curve. So if this is applied to the tangent vector of the curve, then this curve must be a geodesic. A weaker condition to define a geodesic is that the rate of change of the tangent vector along the curve is not zero, but it is proportional to the vector itself. So it is parallel, it is transported parallel to itself again. But this is not really a new condition because, as we will see, by using an appropriate reparametrization of this condition, we can set the condition equal to 1, to equation 1. So if we define a geodesic by a tangent vector that is kept constant along the curve, then the parameter of that curve is called an affine parameter. From the definition we see that if tau is an affine parameter, then alpha tau plus beta for given real constants alpha and beta also defines an affine parameter on that curve. And as physicists, we are quite happy with this property, since this just corresponds to the choice of unit of length or time along the curve and the origin of measurement of such length or time. From the definition of the geodesic, if we choose a particular coordinate system that gives us Christoffel symbols gamma mini rho, this equation can be written in this form. And if x mu are the coordinates of this coordinate system, then v mu is equal to the rate of change of those coordinates along the curve. And we can substitute them in this equation to obtain this equation in terms of the derivatives of x along the curve. Now the first term is nothing but the second derivative of the coordinates. And we see that this is a second order differential second order set of differential equations for the functions x mu. And if those functions are given at a specific point, and we know the rate of change at that point, this will give us a unique solution. So we are led to conclude that if we have a point P and a vector at that point, that determines a unique geodesic through P with tangent vector V. From this equation, we also see that the solution depends only on the symmetric part of the Christoffel symbols. So torsion will not change the geodesics of the manifold. If the gammas are zero everywhere, then the solutions of those curves are straight lines. This property is only of flat spaces, so we conclude from that flat space geodesics are straight lines. Free particles move on geodesics. That is a postulate that comes from the equivalence principle. If we are an observer that is defined by a set of inertial frames, then we should see free particles to move on straight lines locally in our lab. Of course, that will be true in a small region, small enough that the effects of curvature are not seen. But if we put all those straight lines, the one after the other, then a geodesic must be constructed. So here is where the postulate that free particles move on geodesic, the geodesics come from. If a particle is not free, and there is a force acting on it, then we can add it on the right-hand side of this equation. This example here shows us the force acted on a point charge Q by an electromagnetic field given by F mu nu. We also notice that the character of the geodesics, whether they are time-like, null, or space-like, cannot change along the curve. And that comes from the fact that metric-compatible derivative operator preserves the inner products, as we have seen in the previous video. So this inner product cannot change sign along the curve. Now let's see what happens to the geodesic equation if we change parameter. If tau is an affine parameter and s is any other parameter which is a function of tau, then we can compute the terms that are in the geodesic equation with respect to tau. dx d tau is given by dx ds ds d tau, and the second derivative must be taken with care. Dx d tau here must be substituted by ds d tau dx ds, and the chain rule substitutes d by d tau. So we apply the Leibniz rule in this product. We obtain those two terms, and we notice the first term is nothing but the second derivative of s with respect to tau. We go back with the chain rule, and we write ds d tau d by ds as d by d tau. So that is the second derivative of s with respect to tau, and we put it here. Now the other term here involves the square of the first derivative of s with respect to tau. So if we take the geodesic equation with respect to the affine parameter tau, this should be equal to 0, and if we substitute the second derivative and the first derivative, we obtain this equation shown in the right hand side, and we factor terms by taking ds by d tau square, common factor between those two terms, and then we have a term here that remains that involves the first derivative of x with respect to s. So we can write down this equation as this left hand side be equal to this right hand side, and we see that the left hand side is nothing but the directional derivative of v prime, and we see that instead of this being 0, this is proportional to itself, as promised in the first slides of this video. So this function here that gives the proportionality of the parallel transport is given by the second derivative of s divided by the first derivative squared. If we consider time-like geodesics, we know that for any time-like path, u mu is the forward velocity of a particle of mass m. Tau is taken to be the proper time, and then the momentum of that particle is m times its forward velocity. So the geodesic equation can be translated in an equation involving the momentum of the particle. Now if we have photons, they move on null paths, and for those geodesics, we pick a particular affine parameter such that dx by d lambda is giving the momentum of the corresponding photon. If we have an observer that has forward velocity u, we know that it measures the energy of that photon to be p mu u mu. Time-like geodesics, we will see that there are local maxima of proper time with respect to all curves connecting to neighboring events. But we will prove that there are local extrema, but we can see that these are local maxima and not local minima, because any time-like geodesic is infinitesimally close to a null curve. So you see this is a time-like geodesic, and this is a null curve that is like this zigzag time. Of course, if you don't like the corners here, you can make them, you can smooth them out. It will not change the conclusion. So you see that this cannot be a minimum of proper time, because there is always a curve nearby that has length equal to 0. Now these extrema will be local extrema, and the reason for that is that global topology may have 2 points be connected by more than one geodesic. In flat space, we know that any 2 points are connected by a unique geodesic, a straight line. But we already know, for example, if we live on a sphere, then the geodesics are the maximum circles, like an equator. And if we consider 2 points on that circle, there are 2 geodesics connecting them. One that has the small length and one that has the longer length. Here we show a less trivial example on a cone, and we see those 2 points that are connected by 3 different geodesics. They are both local minima for curves that are connecting those 2 points, but you see those 3 have completely different lengths, and only the blue one is the absolute minimum. Now let's see why geodesics are curves that extremize the length of proper time of curves connecting to 2 points, to events. We will discuss time-like geodesics and time-like curves connecting 2 events, but the discussion follows the exact same steps if you want to consider space-like curves. So for a time-like curve, the space-time length is given by the proper time along the curve, and the finite proper time of a curve connecting 2 points is just the integral of d tau, so that is the square root of this quantity here, which gives d squared minus d squared. So if you want to see the variation of the proper time compared to nearby curves connecting the same 2 events, then this can be computed by varying the integrand inside the integral. Now, the variation of the square root is trivial, because the square root can be varied first and give us here 1 over square root of this quantity times the variation of g nu nu dx nu. But we can always choose a parameter where for all nearby curves, this quantity remains the same and equal to -1. So we will consider variations where the value of this square root is always equal to 1. So we can ignore it in the variations. So all we have to do is to vary this quantity here in order to extremize the proper time. So what we do is we consider two events here, one event here, one event there, and all possible time-like curves that connects them. So let's say that they're close enough so that there is a unique time-like geodesic connecting them, and all nearby curves, which are not geodesics, are differing from this geodesic by delta x mu. Now, with this variation, the metric on the neighboring curve also changes, and if we consider infinitesimal variations and we do a Taylor expansion, the components of the metric differ from the value of the components on the geodesic by this amount, which is linear in delta x lambda. We ignore all higher order terms. So now we vary this term. We have three factors. So we apply the Leibniz rule, and the variation acts on each one of them. Delta g, delta dx d tau, delta dx d tau. First, we notice that because of the symmetry property of g, those two terms are the same, just by relabeling the dummy indices. So we have 2 times g mu nu, delta x mu d tau, delta d by d tau, delta x nu. Now, for the first term, this is the variation of the metric, so we substitute for it here. And now we will do a partial integration so that we will factor out the variation delta x nu. So let me remind you how to do that in these variational games. So we have this term involving the derivative of the variation, and we can write that as the total derivative of the term minus the derivative acting on everything else but the variation. Now, this is a boundary term because it is a total derivative, and it is just given by those two terms. But because we choose variations that leave the endpoints of those curves to be fixed, delta x is equal to 0 at the two endpoints. So this term here, those two terms here vanish. So we can ignore this term altogether. So we can do the partial integration and move the derivative from delta x to the other factor here. And then you can see that we can factor out delta x just by relabeling the indices on the first term. So we change lambda to nu and nu to lambda to obtain this expression here, and delta x nu can be taken to be a common factor. So here we have the derivative d by d tau acting on this product. Then we have those two terms, the derivative acting first on g and then acting on dx d tau, giving us the second derivative. But d by d tau of g is dx d tau times the partial derivative of g with respect to x lambda. So we also obtain here d lambda g mu nu, like we have on the first term here. And then we have two first derivatives here, dx mu, dx lambda. And now notice that this term here is symmetric under the exchange of mu and lambda. So we can write this as a sum of d lambda g mu nu plus d mu g lambda ni, and see that both those terms are equal to this one under the relabeling of the indices of the symmetric product dx mu dx lambda. So, since extremization is for our arbitrary delta x nu, that implies that the integrand is also equal to 0. And of course you are very used to that when you do variations of the action in classical mechanics, but let's remember why this is true. Since this is true for any variation, we can take this limit of where the variation is only non-zero at a particular point, and then do that for all such variations. So then the integrand here will be 0 at all points along the curve. So we will get rid of this g mu nu here to get the geodesic equation. So we multiply with the inverse metric here, g sigma mu. So it acts here and there. But this is done so that this gives us a Kronecker delta, delta sigma nu, which will give us the second derivative of x sigma. And now you see that this term here is nothing but a Christoffel symbol gamma sigma mu lambda. So that's the geodesic equation. And we see that proper time is extremized for functions that satisfy the geodesic equations. And because of their uniqueness, then geodesic equations extremize proper time. Now let's move on and discuss Riemann normal coordinates. As we have already discussed in the previous video, the Christoffel symbols are 0 everywhere, only on flat manifolds. So, but we can also choose particular frames at a given point where gamma vanish at that point, and that will give us inertial frames. Let's make such a construction using geodesics, and that will give us the Riemann normal coordinates. First, pick an event in space-time and consider all geodesic going through P. So every vector here will give us a different geodesic that goes through P. Now, after choosing a vector V and the geodesic that has an affine parameter lambda, let's consider a point on the manifold, not on the tangent space, that is found on the geodesic, that is defined by P and V, and the affine parameter lambda, that is at a distance, at an affine parameter distance lambda along the geodesic. So that will give us a point Q on the manifold. Note that we will obtain the same point on the manifold if we had chosen the geodesic that is defined by vector, let's say 2v, and found a parameter lambda over 2. So we will fix this arbitrariness by considering points in the neighborhood of P that are at lambda equal 1 affine parameter away from P. So if we consider a neighborhood of P that is small enough and the effects of the curvature are not so strong as to make geodesics to intersect, then we have a one-to-one map between some of the vectors in the tangent space and the points in that neighborhood of P. Next step is to consider an orthonormal basis at the point P. That means that the inner product of any two members of that base is equal to eta mu nu, and then define x mu to be the components of V in that basis. Now we postulate those components to be the coordinates of Q in the Riemann normal coordinates. So for a small enough neighborhood around P, this will give us a well-defined coordinate system. Now, one can show, and you can open the heavy book by the three giants of gravity and look at problem 11.9 to see how this is proved, that if you make such a construction, then the orthonormal basis mu is the value of the coordinate basis of that coordinate system at the point P. And in those coordinates, the Christoffel symbols at the point P vanish. Now there is a less trivial property of this coordinate system that states that the first derivatives of gammas at the point P is given by the components of the Riemann curvature tensor. We have not defined that yet, we will see that in the following video, but this tensor here defines what is called curvature in a manifold. So those properties also mean that g nu nu at the point P is equal to eta mu nu, that the first derivatives of g vanish at the point P, and the second derivatives of g are given also by similar components of the Riemann curvature tensor. Just notice that this mu index here has been put downstairs here, so these and these are not the exact same values, so we have to lower this index to obtain this expression. Now, an even more interesting property is that we can write down the components of the Riemann tensor at the point P as this very simple expression of involving the second derivatives of g at the point P. And as we will see, it is quite tedious to compute those components. So this is an extremely simple expression, valid of course only at the point P and not elsewhere. Now, if you consider any normal coordinate system that differs from the Riemann normal coordinates at second order, then this will have all those properties except those involving the Riemann tensor. But if you define any coordinate system that differs with respect to the Riemann normal coordinates to third order, then you have all those properties to be preserved. So we have seen that if we have parallel transport defined on a manifold, this defines geodesics. Let's see now how geodesics define a parallel transport and a torsion-free covariant derivative on a manifold. Assume that we know all geodesics on a manifold M. Then we can construct a parallel transport using the so-called Shild's ladder. Let's see how this construction works. First, consider any curve here, gamma, not necessarily a geodesic, and the point P0 on it. Now, let W be a vector at the point P0, and consider the known geodesic passing through P0 in the direction of W. And let W0 be a point on the geodesic that is infinitesimally close to P0, but on that geodesic. So we can write down, not in a very, of course, rigorous way, that P0 W0 is equal to epsilon times W at the point P0. So if you're not very happy with it, think as a physicist and in terms of the equivalence principle, where vectors and straight lines, or sorry, line segments are identified in a flat space. So this is approximately true infinitesimally close to P0. So now let's move on and consider a point P1 that is also infinitesimally close to P0, and of course on the curve gamma. Since we know all geodesics, and all those points are infinitesimally close to each other, we can draw the unique geodesic connecting the point P1 with the point W0. So this red line here is part of a geodesic. Then consider the point N1 that is standing midway between P1 and W0. That means it lies on a geodesic at an affine parameter lambda N1, which is the midpoint of the affine parameters of the respective points, P1 and W0. Now we can draw the unique geodesic that connects P0 and N1. We know all geodesics, therefore we can choose this among all possible geodesics in the manifold. And now what we do is we extend it to reach point W1 so that N1 is midway on that geodesic between P0 and W1. So that will give us a unique point W1. We define the vector, the infinitesimal vector P1W1, to be the one that is parallel transported from P0 to P, that is the parallel transport of P0 W0 along W to the point P1. Next, repeat this construction. Choose a point P0, P2, close to P1, draw the geodesic connecting P2 and W1, find the midpoint N2, draw the geodesic P1 and 2 and extend it to W2 so that N2 is midway between P1 and W2, and then P2 W2 is parallel to P1 W1, and P1 W1 is parallel to P0 W0, so P2 W2 is defined to be parallel to P0 W0. And continue. Choose a point P3, define P3 W3, which is parallel to P0 W0, then repeat for P4, and so on as many times as you want. So this, you see that it works for flat space. If you do this construction on flat space, and all these are straight lines, then you see that indeed you construct line segments that are parallel to each other in a trivial way. Now we assume that this works also for curved spaces over infinitesimal distances, and we use the equivalence principle to argue for that. So if we integrate this procedure, we can define parallel transport on the curve gamma over finite distances. So the vector W at T0 can be parallel transported to a point on the curve given by the parameter T, which we will call tau T0T of W T0. And you see that this construction can be reversed and get back to the same point. So WT can be transported back to T0 using the same construction. So if you have W at the point T0, you can use Shild's ladder to parallel transport it to the point given by the parameter T and compare it with the value of the vector field at the point T. So by doing this comparison, you can compute the derivative. Now, you can check that this parallel transport has the desired properties that we postulated in the previous video, namely that Fw is parallel transported to F times the parallel transport of W, and the sum of two vectors parallel transported is equal to the sum of the parallel transported vectors. So we can define a covariant derivative like we did in the previous video. We take Wt, we transport it back to the point T0, we compute the difference here, take the limit, and that will give us a definition of a covariant derivative. And for it to be a covariant derivative in the sense that we have formally defined it in a previous video, it must have properties 1 through 5. Now, properties 1 through 3 are quite easy to prove, and I leave it to you as an exercise. Now, properties 2 and 4 imply 5. So, we have already done this we have already proved that before. So, what we will do is we will prove 4, and that will also prove 5 by using property 2. So, consider two vectors at the point t0 on the curve, and the curves to which they are tangent to. And let's consider infinitesimal motion on those integral curves given by this small parameter epsilon. So as we move along the integral curve of v, we go from this point to epsilon v, and in this direction we'll go to the point epsilon w. Now let's use Shild's ladder to parallel transport epsilon w to the point that is defined by epsilon v. So you see the construction here, and it will give us the vector which is epsilon times tw, because of the property of the parallel transport. Epsilon can be taken out here, and repeat the same process for parallel transporting epsilon v along w to the point epsilon w. Now you see that this parallelogram here closes because of this construction here. And let's consider the values of those vector fields at those neighboring points. Of course, these values differ from the parallel transported vectors here, so it will be something different. So let's say that w t0 plus epsilon is the value of w at this point, and also multiply it by epsilon to make it infinitesimal. And we do the same thing for v, and we obtain epsilon v here to be this vector. Now, the difference between the values of the vector fields at the neighboring points compared to their parallel transported values is proportional to the derivative that we defined before. Now, since this is epsilon times the vectors, this difference here is epsilon squared times the directional derivative. And similar here, for the difference between v and tv, we have epsilon squared times the wv. Now, do this mental exercise and convince yourselves that this is the correct sign here. It's not so hard. Now, if you consider the difference between those 2 points, this is nothing but the difference between those derivatives here. So that is epsilon squared dvw minus dwv, this vector here. But we have seen in a previous video that the closing of this rectangle here, that does not involve parallel transport, just the values of the vector fields, is proportional to the commutator of the vector fields. And this here is proportional also to epsilon squared. So actually, the commutator here is equal to dvw minus dwv. And we have shown that property 4 is valid for this definition. So let's apply this to an expanding universe. We will consider again flat space cosmology as we did in a previous video. The metric for this cosmology is given by this expression here. We see that space is flat at a given time, x, y, and z are Cartesian coordinates for those observers here. They're called co-moving observers. And this sum here can be written as, with the help of a Kronecker delta, delta ij, as delta ij dxi dxj. So the first step is we will calculate the Christoffel symbols, and we will follow an orthodox part without applying the the formula that involves the derivatives of the metric, by taking a shortcut that involves the extremization of the lengths of curves, as we did for showing that geodesics are curves of extremal proper time or length. So here is the length, the proper time, that's proportional to the proper time square of this of such a curve. And what we will do is to compute the variations of this integral with respect to changing the x mu's. First, we will consider variations with respect to the parameter t. Now, when varying this expression here, we see that the only time-dependent factors are the first term and a square, which is a function of t. So delta a is given by a dot delta t. Therefore, the variation of the integral here is given by varying the first term, gives us 2 times dt d tau times d delta tau by dt. And here we have just the variation of a square. That is equal to 2 times a dot delta t. And we also do a partial integration like we did before. Here are the details. And assuming that the variations of t vanish at the ends of the curves, then this term vanishes, and we end up only with this term in the integral. So delta t now can be taken as a common factor, and this is the integrand here. And if the variation is 0 for any delta t along that curve, that makes the integrand here to vanish. So that is the equation of the geodesic, and if we compare it with the geodesic equation involving the Christoffel symbols, we can read off their values. So you see here that we have only special derivatives, dxi and dxj. There are no dt terms here. So all the Christoffel symbols involving time here vanish. And the only non-zero terms are the ij terms, and they're equal to a dot, coming from the comparison of those two equations. In order to compute the other Christoffel symbols, we consider variations of the spatial coordinates. xi goes to xi plus delta xi. So the first term here does not vary under this variation, only the second term varies, and now a is assumed to be a function only of t, so there's no variation of a square, but we vary those terms involving the derivatives of x. Now, because of the symmetry of the Kronecker delta, those two terms are equal. Just relabel I and j here. So that will give us this term here. And by performing a partial integration, we change the sign, and we obtain the derivative of a squared delta ij dxi d tau by d tau. So again, this is true for arbitrary variations, therefore the integrand must be equal to 0. And if we compute the action of the derivative on those two factors here, we have those two terms, one acting on A and giving us dA d tau, and the other one giving us the second derivative of x with respect to tau. So this is the equation of the geodesic in this space-time, and let's write it here in a trivial way. We have two terms, dt dxi and dxi dt. And now we have to compare this geodesic equation with the one involving the Christoffel symbols. Now let's be careful a little bit, because here the index is I, but the lower indices are summed over all possible values of mu and nu, including 0. So we have those four possibilities, one having 0, 0, dt dt, 0j, dt dxj, j0, dxj dt, and jk, dxi dxk. So we have to compare those terms with this equation here. Now we see that the equation we just derived has only dt dxi terms. So the 0, 0 terms here and the jk terms must vanish. So gamma I 0, 0 and gamma I jk must be equal to 0. And gamma I 0j and gamma I j0 must be equal to a dot over a. So let's use now these values of the Christoffel symbols that we computed in order to compute null geodesics. And for simplicity and without too much loss of generality, let's consider trajectories of photons along the x-axis. So we will confine ourselves to the case where y, the functions y of lambda and z of lambda are equal to 0. So since geodesics are null, ds square vanishes, so minus dt square plus a squared dx square must be equal to 0. So we can solve for dx by d lambda, that is equal to 1 over a dt d lambda. You see we chose the plus sign because we consider motion of photons along the plus x direction. If you want the minus x direction, just choose the opposite sign. And by inserting the values of the Christoffel symbols that we computed before, we have the geodesic equation written in this way for d squared t. So we have d squared t by d lambda square, only this term survives here, a dot dx by d lambda square. And then we can substitute dx by d lambda by 1 over a dt d lambda using equation 1. So we have this equation here, and this gives us this differential equation of t as a function of lambda. The solution of this equation is easy to compute. Just substitute to convince yourselves that omega 0 by 8t is the solution of this equation. Omega 0 is an arbitrary integration constant. Now a of t is a known function. It's a solution of Einstein's equations. And therefore equation 3 can be integrated and give t as a function of lambda. Having t as a function of lambda, we can go back to equation 1 and compute x as a function of lambda. We will not do that, it's not so interesting. Now let's consider co-moving observers. These observers have 4 velocity, which is equal to 1, 0, 0, 0. So the energy of such photons moving on those curves is given by P mu U mu. So this is just G00, dx0 lambda U0, and if we substitute those values, U0, UC is equal to 1, and this is simply just omega 0 by alpha, by A. So omega 0 is the frequency of the photons when A of t is equal to 1. So this is, of course, arbitrary. We choose a value of the time coordinate where this is true in some units. So we can compute the cosmological redshift of photons along such a curve, and we see that E2 by E1, which is related to their frequencies, is just given by A1 by A2. So the energy reduces. That affects, of course, the wavelength of the photon, but don't confuse it by, the fact that the expansion of space stretches the wavelength. It is just a fact of the quantum mechanical connection between energy and frequency.